Now we will discuss the topic 2, which is fins. Fins is nothing but an extended surface on a component is known as fins. If you remember the Newton's law of cooling is Q dot convection is HA Ts minus T infinity, where HA is the convective heat transfer coefficient, A is the surface area, Ts is the surface of temperature of surface, and T infinity is the temperature of surrounding fluid. Let us say if we want to increase the rate of heat transfer due to convection or rate of heat transfer, then it can be done by either increasing convective heat transfer coefficient or surface area or Ts minus T infinity. But the temperature difference is a constraint because the base temperature and atmospheric temperature is fixed. So this is not a solution, and as we know, the convective heat transfer coefficient is dependent upon geometry of surface, orientation, flow properties, that is velocity, and fluid property such as mu is nothing but viscosity, specific heat, and thermal conductivity. So it is very difficult to control the convective heat transfer coefficient. The only thing left with us is area. We can increase the area, by providing some extended surface. On component, and this extended surface is known as fins. So the function of fin, function of a fin is to increase the rate of heat transfer. Let us say this is our fin. Okay. And it's something like this. Okay. This surface is known as the base surface, from where fin starts, and its temperature is known as base temperature. Let us say the x axis is along the fin. So consider a volume element of thickness delta x at a distance x from base. So this is our volume element. Okay. This one is our volume element. If we draw the volume element in enlarged view, we will get something like this. Okay. If I draw like this, okay, we will get so. Now let us say this is A, this is B, this is C, this is D, this is E, F, G and H. So if we see here, the convection can happen from the top surface, bottom surface and the two side surfaces. Now concentrate on the volume element. What will happen? Some amount of heat will come from the base and it will come via conduction at distance x, and from the cross section it will leave the volume element. Let us say this is x plus delta x. From the top, bottom and two side surfaces it can convect, so there will be one convection heat transfer. And let us say cross sectional area of this fin is AC and the perimeter of the cross section, perimeter of cross section is P. So if we see here, surface available for convection is top surface, that is ADGF, bottom surface, that is BCHE, and two side surfaces AB, EF and CD, GH. So the total surface area available for convection is equal to 2 times of AB into BE, or you can say delta X plus twice of BC into delta X. Delta X is the thickness of this volume element, this thickness delta X, and we can write this as AB plus BC into delta X. And if you see properly, this is nothing but the perimeter of cross sectional area, P into delta X. Now apply energy conservation equation. With assumptions first one, steady state heat transfer. Second one is convective heat transfer. Coefficient is uniform and constant over the surface. And thermal conductivity K is constant. If we apply the energy conservation equation, we will get Q dot conduction at x plus delta x minus Q dot conduction at x plus Q dot convection is equal to 0. And if we go on further and simplify this, we will get Q dot x plus delta x minus Q dot conduction x upon delta x plus Hp T minus T infinity is equal to 0, where T infinity is the temperature of fin surrounding. Okay. And now if we take the limit, we will get dq dot upon dx plus hp t minus t infinity is equal to 0. Now assume theta is equal to t minus t infinity, that is d theta upon dx is equal to dt upon dx. This implies d2 theta upon dx square is d2t upon dx square. And also q dot conduction at x is nothing but minus KAC dt upon dx. This implies minus KAC d theta upon dx. So if we substitute all these values in this equation, we will get d2 theta upon dx square minus m square theta is equal to 0. This is known as the fin heat transfer equation or fin equation. Let us say this equation is 4. So in equation 4, m is equal to root of hp upon KC, and solution of equation 4 is c1 e to the power mx plus c2 e to the power minus of mx. To get the unique solution, we need two boundary conditions, and depending upon the types of fin, the value of c1 and c2 will change. So the first kind of fin is infinitely long fin. That is, the temperature of the fin tip will go towards the atmospheric temperature. So the two boundary conditions are at x equal to 0, that is at theta base, theta is equal to theta b, and as x tending to infinity, theta tending to 0. If we substitute this boundary condition into this equation, we will get c1 is equal to 0 and c2 is equal to theta b. and hence the temperature distribution is theta b to the power minus of mx. Let us say the y coordinate represents temperature difference and x represents the fin length. At x equal to 0, the temperature difference is theta b. As we move towards x, it will tend to go towards 0. Okay, so the temperature variation inside an infinitely long fin is exponential. And the rate of heat transfer through fin can be given as minus KAC d theta upon dx at x is equal to 0. If we do this, we will get as HP K AC Q dot long fin into theta b. The second type of fin is adiabatic fin tip. What do we mean by adiabatic fin tip is there is no heat loss from the fin tip, that is Q dot fin tip is equal to 0. So the two boundary conditions for adiabatic fin tip is at x is equal to 0, theta is equal to theta b, and at x is equal to L, where L is the length of fin. L is length of fin. D theta upon dx at x equal to L is equal to 0. If we substitute these two boundary conditions into the general solution of fin equation, we will get C1 is equal to theta b upon 1 plus e to the power 2 ml, and C2 is equal to theta b upon 1 plus e to the power minus 2 ml. So the temperature distribution or temperature difference distribution inside a adiabatic fin is given as theta is equal to theta b times cos hyperbolic m L minus x over cos hyperbolic ml. And the rate of heat transfer through a adiabatic fin is given as minus KAC d theta upon dx at x is equal to 0, which is equal to root of HP KAC theta b 10 hyperbolic ml. Adiabatic fin. The third kind of fin is a specified temperature at tip. Let us say this is my fin, and with some instrument I can measure the temperature of the tip. Then this kind of fin comes under this type. A specified temperature at fin tip, and this surface is known as best surface as we have discussed earlier, and its temperature, let us say it is Tb and tip temperature is TL, and let us say the temperature difference, we denote it as theta b and temperature difference as theta L. So the boundary conditions are at x is equal to 0, theta is equal to theta b, and at x is equal to L, theta is equal to theta L. If we substitute these equations into the general equation, we will get the value of C1 and C2, and the temperature variation will look like theta upon theta b is equal to theta L upon theta b sine hyperbolic mx plus sine hyperbolic m times L minus x upon sine hyperbolic ml. And the rate of heat transfer through a specified temperature fin tip of fin is given as minus KAC d theta upon dx at x is equal to 0, and which is equal to root of HPK AC times theta b cos hyperbolic ml minus theta L upon theta b divided by sine hyperbolic ml. Rate of heat transfer through this kind of fin. And the fourth and last kind of fin is known as the convective fin tip. That is, let us say if this is my fin, we are seeing that the fin tip is doing the heat transfer via convection. So the boundary condition for this kind of fin is, and we know the base temperature, obviously theta b. Okay, so the boundary condition is at x is equal to 0, theta is equal to theta b, and the second boundary condition is q dot convection at x is equal to L is equal to q dot conduction at x is equal to L. That is minus KAC d theta upon dx at x is equal to L is equal to HA temperature of the fin at the distance L minus T infinity. If we substitute these two boundary conditions into general equation, we will get the values of C1 and C2. Afterwards, we will get the temperature distribution inside the fin as theta upon theta b is cos hyperbolic m L minus x plus h upon mk sine hyperbolic m L minus x upon cos hyperbolic ml plus h upon mk sine hyperbolic ml. And the rate of heat transfer through the fin q dot convection fin is given as root of HPKAC into theta b multiplied by sine hyperbolic ml plus h upon mk cos hyperbolic ml upon cos hyperbolic ml plus h upon mk sine hyperbolic ml. Till now we have discussed four kinds of fin. Now we will discuss the efficiency, fin efficiency, and fin efficiency is defined as the ratio of actual heat transfer from fin to maximum heat transfer from fin if entire surface were maintained at fin base temperature. Let us say this is the fin. In the actual case, the fin surface temperature will go down as we move from base to tip. Let us say if the base temperature is 80 degrees centigrade and the surrounding temperature is 25 degrees centigrade. So the temperature somewhere here will be 70 degrees centigrade. As we move towards tip, it will again drop and so on. But if we want to get the maximum amount of heat transfer from a fin, the ideal condition should be all the fin surface should have a uniform temperature, let us say 80 degrees centigrade at all the surface. In this case, the heat transfer from the surface will be maximum. So heat of fin is defined as Q dot actual upon Q dot ideal, and Q dot ideal can be given as HAS into theta B, since all the surface is maintained at base temperature, and this is equal to H into PL theta B. AS is the surface area available for convection, and we have derived this as P into L, where L is the length of fin. Now consider infinitely long fin. Long fin, in that case Q dot actual is given as root of HPKAC theta B, and the ideal is HPL theta B. If we simplify this, we will get this as 1 upon ml. So the efficiency of an infinitely long fin is given by this formula. Similarly, we can derive a fin efficiency formula for an adiabatic fin, okay, and it comes out to be 10 hyperbolic ml upon ml. If you consider some of the facts about fin efficiency, as we increase the conductivity of fin material, efficiency of fin also increases. Now the second term in the fin that is important is the effectiveness of fin, right? We use the fin to increase the rate of heat transfer. So to check whether inclusion of a fin is increasing the rate of heat transfer or not, we define a term effectiveness, and it is defined as ratio of heat transfer with fin to without fin. Let us say one surface which has fin and another same surface won't have any fin, and this is the cross sectional area, right? So the heat transfer without fin can be given as HAC into theta B, right? Only due to convection, and AC is the area available for convection. Effectiveness is denoted by epsilon, and this is equal to heat transfer with fin upon heat transfer without fin. If epsilon, that means effectiveness, is greater than 1, then we say that rate of heat transfer has increased, right? So for effectiveness of a long fin is given by root of Pk upon HAC, and the effectiveness of an insulated or adiabatic fin is given as root of Pk upon HAC tan hyperbolic ml. Some of the conclusion from the formula of fin is conclusion from the effectiveness. First is value root of Pk upon HAC should be greater than 1, and strictly saying a provision of fin on a surface is justified if root of Pk upon HAC is greater than 5. Okay. The second one is for effective fin, should be as thin as possible and closely spaced. And the third one is thermal conductivity of the fin material should be as high as possible.